Hello, and welcome to our first ever online lecture. Today we're going to focus on the topic of energy. Now, all types of things have energy. There are many different forms of that concept. Today we're going to focus particularly on two different types, and specifically, how can you quantify or calculate that energy? So if we look at energy, there's, like I said, different types of it. Usain Bolt here has energy of motion because he's moving at about 7.67 meters per second. This dude on top of a diving board has energy of position due to his position and gravity, based on the fact that he is 3 meters up in the air. Now, we could quantify both of these energies to compare them to each other, even though they are different types of energy. I'd like you to make a prediction in your head right now, looking at these two different objects, these two different people, and predict who has more energy in this picture, person A or person B. We will come back to this example in a little bit once we have learned how to quantify and calculate these energies. Now, as I mentioned, there's many different types of energy, and depending on the topic that you are studying in science, whether it's chemistry or biology or different levels of physics, you will encounter many of these different forms of energy at some point in your scientific career. Today, we're going to focus specifically on these two down here, kinetic and gravitational energy. These fit under an umbrella term that we say is mechanical energy. Energy of motion and position based on a physical object with mass. Kinetic energy, or the energy of motion, can be calculated using the equation kinetic energy is equal to 1/2 times the mass times the velocity squared. Now, we don't usually write this out in words, so instead, we'll write it in symbols, where kinetic energy is Ke, that's equal to 1/2 times the mass, which is lowercase m, times the velocity squared, v squared. So we say Ke is equal to 1/2 mv squared. Now, each of these properties has their own particular units, and they are units that we have identified before for the most part. So velocity we're going to find as meters per second. That's pretty standard. Mass, we're going to use kilograms, which is our SI unit for mass. Now be very careful. A lot of times when we are dealing with something, at least something on the smaller range for like a lab, we'll typically have a mass in grams. In order for this equation to give you what you want, you must convert that mass into kilograms. Now, if we take that kilograms times meters per second squared, we will end up with a unit of energy. This is a derived unit, and the unit that we use is called joules, Joules. That joules is given to us as an abbreviated form of just a capital J. We'll see that in a little bit in a couple different examples. So if I wanted to use this in a calculation, using that equation is pretty straightforward. If I wanted to calculate the kinetic energy of a truck that's 1,500 kilograms, that's moving at 18 meters per second, first, I can define these two different numbers. 1,500 kilograms, that is the mass. 18 meters per second, that is the velocity. And of course, my equation is 1/2 times the mass times velocity. So if I plug in those values, 1,518, making sure to square it, that's the easiest thing to forget, I can plug that into my calculator and find that overall, this truck has a total mass of 243,000 joules. Total energy, rather. I said mass before. That's a lot of energy. And part of the reason is because mass is in this term, and this truck has a lot of mass. So with that form in mind, we don't always have to calculate the kinetic energy. We could use this equation to solve for any of the terms in here. We could solve for mass, or we could solve for velocity as well. So I would like you to try one on your own. A bowling ball travels at 2 meters per second down a lane with 16 joules of kinetic energy. I would like you to use this information to find the mass of the bowling ball in kilograms. All right, now that you have had an opportunity to try that, let's look at the numbers here. Kinetic energy is 16 joules. The velocity is 2 meters per second. Again, kinetic energy is 1/2 mass times velocity squared. And if I wanted to calculate that for mass, I can rearrange this equation, multiply both sides by 2, and then divide both sides by v squared. So I get that the mass is equal to 2 times kinetic energy divided by the squared value for the velocity. Plugging in my numbers, 2 times 16 is 32, divided by 2 squared is 4, 32 divided by 4 is 8 kilograms for the mass. So that is kinetic energy. There is another form of mechanical energy that is important to us, and that's based on its position and gravity. Now, if we have two people standing on the same diving board, I'd like you to predict of these two, who has more potential energy? Who has more energy that is stored up? Because you can probably figure that out just by looking at it. This person over here, the sumo wrestler, probably has more energy if they're up on the same diving board. And the reason they have more energy is because they have more mass. If we look at a slightly different example, here we have a ball that is pulled up on its pendulum rope, and we have position A and position B. Same ball, same mass. Position A is just higher. I'd like you to predict which has more potential energy. And you could probably predict this as well. A has more potential energy, is more energy that's stored up if you pull it higher on that pendulum, and the reason it has more height. Now, if we factor these two things in, mass and height, we know that the energy must be directly related to these two quantities. We can calculate the potential energy, taking the mass times the gravity times the height. Again, we don't usually write this formula in words. Instead, we write it in symbols. So we say PE for the potential energy is equal to mass is m, gravity is g, and height is h. Now, each of these has its own units as well. Height, we will typically measure in units of meters. Gravity, we've actually seen before in a couple different units now, for force and for motion. Gravity is the acceleration of gravity, or 10 meters per second squared. In this particular case, we are going to use a positive 10 meters per second squared because we don't worry about the direction when it comes to energy. Energy is a scalar quantity, which means it is always positive, can never be negative. Finally, on the right hand side here, mass is calculated in units of kilograms. And then potential energy, just like kinetic energy, is measured in units of joules. This will allow us to compare potential and kinetic side by side. Let's look at a couple examples here. If I want to calculate the potential energy of a 3-kilogram bowling ball on top of a 2.5-meter hill, the values that it gives me here are 3 kilograms and 2.5 meters. I know M and I know H. But even though it's not provided in the problem, we're going to assume that this happens on Earth. If it wasn't on Earth, it would tell you, and it would tell you a value for G. Since we assume it's Earth, we're going to assume G is 10 meters per second squared, which means if I plug that into PE is equal to mgh, we have the mass of 3 times the gravity of 10 times the height of 2.5 to give us a grand total of 75 joules of kinetic energy. I would like you to try this next one on your own. Just like we did before, I would like you to use the same relationship to calculate for one of these other variables. In particular, I would like to tell you, like you to tell me how high this grandfather clock pendulum can swing from rest. So if you need to, you can pause the video, or Edpuzzle will pause for you. All right, if we look through this answer, now that you've had an opportunity to try it on your own, we know that the mass is 3 kilograms. We know that the potential energy is 1.5 joules. And again, we're going to assume it's on Earth, so gravity is 10 meters per second squared. Now, potential energy is mass times gravity times height. But if I wanted to calculate for H here, I could do that, just rearrange to say potential energy is, or height is potential energy divided by mass times gravity. Make sure if you're using your calculator to use parentheses around this bottom term so that you're doing order of operations correctly. If I take that to the next step, I can plug in my values. 1.5 divided by 3 times 10, or 30, will give me a grand total of a height of 0.05 meters, which seems like a really small number, but if you think of a grandfather clock pendulum, 0.05 meters is a height of 5 centimeters. Really, a pendulum doesn't swing too high if it's on a really, really long rope, or in that case, its fulcrum is very, very high above the swinging mass. So we can return back to this problem. I would like you to calculate now the kinetic energy for Usain Bolt and the potential energy for this dude on top of a diving board. All right, now that you've had an opportunity to try that, let's check our numbers here. If we want to look for the kinetic energy of Usain Bolt, We can calculate that 1/2 mv squared. 1/2 times 100 times 7.67 squared is 2,941 joules of energy. Now, if I want to compare that to this guy on the diving board, the guy on the diving board doesn't currently have any kinetic energy. Instead, all of his energy is stored up to his position and gravity. So mass times gravity times height, if we plug that in 100 times 10 times 3 is 3,000 joules, which means comparing these side by side, it is much easier to see now who has more energy. This man on top of the diving board technically has more joules of energy than Usain Bolt at his top sprinting speed. Now, you've probably heard this term before, the conservation of energy. And typically, we define the conservation of energy using this famous sentence: energy cannot be created nor destroyed. This just means that energy doesn't go away, it just gets converted from one type of energy to another. Now, the form of conservation of energy that we're going to care about in this particular unit is the conservation of mechanical energy, which means that all of the energy is either kinetic or potential or some combination of the two, that the total energy before will always equal the total energy after. It also equals the total energy at every stage in that journey unless some force was adding energy to the system. So if we look at this guy on top of a diving board, it shows that all of the energy is potential energy, 15,000 joules of potential energy, 0 joules of kinetic energy. If they jump, they're going to start speeding up faster and faster and faster going down, which means that the kinetic energy gets bigger, and since the height is decreasing, the potential energy goes down. Now, I expect that the total energy will always equal that 15,000 joules. So if I look at the bottom, potential is 0, must mean that the kinetic is 15,000. If I look in the middle, potential is 7,500. It must mean that the kinetic is also 7,500 because those two added together will give you that 15,000. Now, these other stages along the way, I can find the difference just to make sure that the total energy, potential plus kinetic, always adds up to 15,000. You may have seen this in a couple different examples before. A classic example is a bowling ball pendulum. So if we were in class right now, we would be doing this in person. But since we don't have that opportunity, I want to show you a video of this in case you've never seen this before. All right, so what's going to happen here is he is going to bring this bowling ball all the way up to this guy's nose. He is currently standing in a spot that he can't move back, but all of this energy is currently stored up as potential energy, which means it will convert into kinetic energy and then swing back up on the other side, convert to potential, swing back to convert to kinetic, and then once again potential. But overall, it will never have more energy than it started with. It will always have that same total energy. Neil deGrasse Tyson is a very famous scientist who's done this example before as well, but very famously in this particular clip, it doesn't work out. That's edited. It's too much fun not to share. All right, finally, I want to end with one example here of a roller coaster. It is the classic example of conservation of mechanical energy, that the energy is provided by this lift hill becomes all potential energy and then converted into kinetic, back into potential, and so on. So I'm going to pull up this simulation, which will allow you to see on this pie chart how the energy is changing. So it's all potential, then turns it kinetic, potential, kinetic, potential, and back. But notice along the way here, it is not always one type. There are many points along this way that it's a combination of the two, but they always add up to that same total pie that was given by this first lift hill. So the potential at the beginning gets converted into these other types of energy throughout. Tomorrow and the next day, we're going to focus more on this concept of how energy can be transferred from one type to another and how we can use that in our equations to calculate for some unknowns.